Today, let's talk about the Grotthuss mechanism of proton conduction and how this mechanism can be useful for proton batteries. First, we need to understand how metal ions are conducted in an electrolyte. Remember, electrolytes do not conduct electrons, but ions. Usually, when ions are dissolved in a solvent. Here we use water as an example. The ions are solvated. In water, they are hydrated. It means that water molecules coordinate the ions, forming a hydration shell. We call these water molecules aqualigands. Such an ion-solvent interaction is called solvation, or hydration if the solvent is water. Both cations and anions can be hydrated in water. Let's look at a hydrated lithium ion first. For the diffusion of this lithium ion, first, its hydration shell, i.e., 4 water molecules around this lithium ion, will move together with the lithium ion as a single species. Second, in order to move the hydrated lithium ion, we'll need to push away water molecules in its way. This ion conduction mechanism is called the vehicle mechanism. Another ion conduction mechanism is referred to as the Grotthuss mechanism. Before we talk about the Grotthuss mechanism, let's take a look at the well-known Newton cradle. Newton cradle is often used to demonstrate the conservation of momentum and energy. Note that the balls need to be homogeneous in its material and elastic. We won't get into the details about how Newton cradle works today. However, it is an excellent analogy for the proton conduction via the Grotthuss mechanism. In the year of 1805, von Grotthuss published his famous paper titled Memoir on the Decomposition of Water and of the Bodies that it holds in solution by means of galvanic electricity. In his paper, Grotthuss described the figure on the right. Here I quote from the paper. It follows that when the water molecule represented by OH yields its oxygen O to the vitreous fluid of the plus where its hydrogen H is at once reoxygenated by the arrival of another molecule of oxygen O', whose hydrogen H' recombines with R, etc. The same thing occurs, but in the opposite direction, ending the quote. We should note that Grotthuss did not know that the formula of water is H2O. He knew that water contained only hydrogen and oxygen. It was in 1811 when the Italian scientist Amedeo Avogadro found the formula for water was H2O. What Grotthuss described in this paper is very close to the modern understanding of the Grotthuss mechanism, named after him. The Grotthuss proton conduction is a cooperative formation breaking of OH covalent bond and hydrogen bonding. When a proton approaches a water chain that is assembled by hydrogen bonding from the left, this proton attacks the oxygen of the leftmost water molecule to form a hydrogen bonding first. This hydrogen bonding is quickly transformed into an OH covalent bond, which causes the ejection of the initially covalently bonded hydrogen of the water, turning that hydrogen into a proton, which in turn attacks the next water molecule on its right. This cascade of conversion from hydrogen bonding to an OH covalent bond and an OH covalent bonding to a hydrogen bonding transports the charge of proton along the water chain from left to right in this case. Eventually, the water molecule on the right end of the water chain ejects a proton out, completing the proton conduction. This process is called structural diffusion, distinct from the vehicle mechanism. My prior student, Dr. Wu Chou-Shin, prepared a cartoon which shows the simulated conduction of a proton from a hydronium via the Grotthuss mechanism to its neighboring water molecules. In this simulation, the final delivered proton is not the same as the initial proton coming from the hydronium ion. The Grotthuss conduction explains why the aqueous acids are often stronger electrolyte than their salty solution counterparts, because water solutions conduct protons faster than metal ions such as sodium and potassium ions. The Grotthuss conduction is well known for the acidic solutions as highly conducting electrolyte. Is it possible to have the Grotthuss mechanism in a solid? The premise is that there needs to be a continuous hydrogen bonding network in the lattice of the solids. Therefore, attention should be given to hydrated materials. Defective Prussian blue is such a material where, due to the significant amount of structural defects, the contained water molecules inside form a hydrogen bonding network that percolates inside the lattice. The left figure is a unit cell of this defective Prussian blue, and the right figure is the water network, the hydrogen bonding network. The next question is whether such a structure supporting the Grotthuss mechanism can help a battery deliver high rate performance. In other words, whether this battery can be charged faster. The answer is yes. My lab conducted the early experiment that tested the power of the Grotthuss proton conduction during the discharge and the charge processes of a defective Prussian blue as an electrode material for proton batteries. The results are astounding. When we increased the charging rate by 1,000 times, the delivered capacity of this battery material is nearly the same. Here 1C means the battery charge or discharge processes is completed in 1 hour. And 1000C means that this same process is completed in just 3.6 seconds. Note that this is a test to approach the theoretical rate behavior of a battery electromaterial, where the electron mass is small. Currently, charging a practical battery device in 3.6 seconds is still very challenging due to the engineering limits. For example, joule heating of the device at a high current. The redox reaction here is so fast that I referred to this reaction as Grotthuss pseudocapacitance. This is all I have for today about Grotthuss mechanism and proton batteries. Thank you.